Cl3. Okay. Well, when you have those three, they want to separate as far away as they can, and it just so happens that they're going to be in the same plane. Okay, so you have a triangle formed, kind of like that, with at your points to your triangle being your chlorine atoms. Okay. So what angle would that be, right there?
120.
120, right?
360 divided by 3.
Exactly. So you have a plane, and it's 120. So if you have the shape is going to be called trigonal because it's a triangle, and planar because it's in a plane. 3 electron domains, and your shape is trigonal and planar, you're going to have 120 degrees as your bond angle. Okay, so let's add a new thing for bond angle. Over here, what's your bond angle?
Yeah, it looks like a triangle.
What would your bond angle be for BeCl2? 180, right? Bond angle is tested on pretty often, actually. It was tested on like every test last year, not even joking.
The important ones to remember are tetrahedral,
Yeah.
trigonal, and linear.
That's what we're going to next, okay? So if you have 4 electron domains,
I could demonstrate.
you're going to have tetrahedral, okay? And we already have gone over this one twice.
Yeah.
So tetrahedral is going to be, let's use methane as our example, CH4, right? And again, if you want to go into the specifics of that, carbon has 1, 2, 3, 4. Hydrogen has 1. And so carbon fills its octet, and hydrogen gets its 2.
It looks kind of like this.
Right? So that works out. So, again, we have that, and Jack showed you how it exists in 3-dimensional space.
All of
So-
these are as far away from the others as it could
This is going to be a hard one to figure out, so I'll be really impressed if someone can guess the exact bond angle for that. Sharik, come on. Come on, you can do it.
Sharik knows.
What?
Close.
109.5. It's close enough. All right, so 109.5 is going to be your bond angle for a tetrahedral structure. Okay?
I'm going to go ahead and draw that out.
Yeah.
This purple doesn't work. Green.
All right.
Green works.
Okay, and now so far, as we're going, can someone tell me what's unique about the examples we have chosen? They're all shared pairs. These are all shared domains. We haven't yet talked about an unshared domain existing, right?
Yeah, like,
So
if
these
you
are-
go on the internet, pretty much every domain's bought by now.
So let's go to 5 shared domains, okay? And
There we go. Can I talk about this for a second?
yeah, go ahead.
So if you look at this, it's like it kind of forms a, one more hydrogen. There we go. So it's like it forms a big pyramid, and this one kind of goes down to there. And it's like a pyramid with a carbon just kind of hovering inside the center. So with the geometry, the way it works, the angle between like any of these two outer triangle bits is going to be 60 degrees, but inside here, between those two, the way geometry works, it just works out to 109.5.
Okay. So, right, that works out. And we'll go into specifics about how to manipulate that shape and predict bond angles in a little bit, okay? So, the next one, we have 5 shared domains, right? We have trigonal bipyramidal. So it kind of looks like a trigonal planar, right? With,
A bit on top and bottom.
yeah, so like you have a trigonal, it's like you have this triangle right here, and then you have like an axis in between where you have 1. You have 3 on the points of your triangle, and then 2 at the poles of your axis going in between it, okay? The axis is going to pass through the center of your triangle right there, which is where your atom X is going to be, right? Okay, so
What it ends up looking like is two triangle pyramids stacked on top of each other.
which is why it's called trigonal bipyramidal, okay? And so let's explore the example of phosphorus pentachloride. So we have PCl5, right? So how many valence electrons does P have? Phosphorus. Come on, guys. Come on, guys. Get out.
3.
Not 3, but 5. Okay, so we'll do
It wants 3.
1, 2, 3, 4, 5. Okay. What about chlorine? Okay. So we have with chlorine.
We get a point.
Oh.
Doesn't that mean we got a point?
that's kind of what we get, right? Can someone point out to me like something that makes you uncomfortable about this right here? So we
The
have.
teacher.
All right, Josh. Not that.
How many pairs do we have? Someone already answer it?
No.
Yeah, how many pairs do we have? Like how many electrons are shared on the phosphorus? 10. How many are there usually? 8.
Does that make you uncomfortable a little bit?
No.
It does?
Well,
Well, suck it up.
what if we take all of the electrons and push them somewhere else? Okay, continue.
Okay. Well, he said the thing is,
Fooling around.
you know that this is right because you really can't have PCl5 exist without having at least a single bond, right?
Yes.
That's a minimum requirement, and so this just has to happen. You'll realize that instead of filling just the S and P orbitals for your valence electrons, this would go into it would flow into your other ones.
So
Or not just that
what Osmond's
last subshell of your S and P.
Yeah, what Osmond's saying is that every single orbital in the valence electrons is used up. And then it'll also start going into other orbitals. Does it go into higher or lower, Osmond?
I actually am not too sure. If it goes
I think it goes into the 5d orbitals of that energy level. Basically, for an electron to be used in reacting, it has to have a half-empty orbital. So in that example there, you have all of your electrons in a free orbital. Chlorine can do this to phosphorus. Since chlorine is a halogen, it's on that 7th row there. And they are really electronegative. And what that means is that they really, really, really like electrons. They are so close to finishing their octet and becoming stable that if there's an atom that can offer one anywhere, it'll grab it and disrupt their stability. Even if it's one like xenon that's already stable, chlorine will try to grab an electron from it.
Same with fluorine too. Fluorine is actually the most reactive element you have for nonmetals, at least.
Yeah.
Okay, so
Sodium and
let's
water.
talk about the bond. Dang, I erased it. Okay, let's talk about the bond angles for this. So we have a bond angle is going to be any angle that is going to be on your that's going to be between atoms that are already bonded.